All right, so now we're going to look a little bit more about metal activity. So the lab activity is all about determining what metals are going to be more reactive. So if we put a metal in a solution, what metal is going to actually react? Is there going to be a reaction? Will we see something occur or not? And we can predict that based on these metal activity series. So the metal activity series is this right here, where we have the most reactive metal up at the top and the least reactive down here. So we're talking about single replacement reactions. So whenever you put a metal in a solution, if the metal added is more reactive than the solution, it will replace it. If the metal is less reactive, then we're not going to see a reaction at all. Well, we can determine reactivity based on the position here on this activity series. So if it's higher up, then whatever you put it in, it will react. So let's do a little bit of practice. Okay, so we're going to be using our activity series that you'll find in your notes and doing our little practice pages here. Okay, so we're going to just underline or circle, whatever, some way that you can mark which one is going to be more reactive. So which one would replace? So this first one says calcium and tin. So we want to look here at our reactivity, okay, at our metal reactivity. And we see that calcium is up here, tin is down here. So because calcium is up top, that means calcium is more reactive. So we're going to circle or underline calcium because calcium is the more reactive one. All right, bromine versus fluorine. Okay, well, fluorine is higher up, so fluorine is going to react. Aluminum versus potassium. Potassium is way up here. Aluminum is down here below it. So that means potassium is going to react. Zinc compared to sodium. So zinc is down here. Sodium is up here. So sodium is more reactive. Okay. So again, we're just looking at where they are on this table. Which one is higher up? Iron versus copper. So iron is up here. Copper is way down here. Iron will react. Iodine versus chlorine. Chlorine is above iodine, so chlorine will react. Silver versus lead. So silver is way down here, lead is up here. So lead will react. And then sodium compared to calcium. So sodium is up here, calcium is up here. So sodium is more reactive. Okay, so again, it's just whichever one is higher up on that list. Okay. So now this was just looking at if we have these two metals together, which one is more reactive. The next part is if we have an actual reaction, can we predict which ones are going to react based on this metal activity series? Okay. So the first thing that we're going to do is we're just going to complete the word equations. So we're not going to try to balance any formulas or write any formulas. We're just writing names. So this first one says zinc and lead nitrate. Well, this is a single displacement reaction, meaning zinc and lead will switch places. So we'll be left with lead by itself and zinc nitrate. Okay, so we're left with lead and zinc nitrate. And now we need to determine, would this actually occur? Would we actually see this reaction? Well, if we look at our table, we see that zinc is here above lead. So we're putting zinc into lead. So yes, because zinc is higher up, it will react. So we're going to circle this equation because yes, that one will react. Okay. The next one, iron and zinc sulfate. So if we've put iron in a solution of zinc sulfate, will that react? So if we do the word equation, we're going to end up with zinc and iron sulfate. So if we look at our reactivity, our metal activity series, we see that iron is below zinc. So because iron is below zinc, it will not react. Okay, so we're looking at when we put the pure metal in a solution, if that metal is above what we put it in, then it will react. If it's below, it will not react. Okay. Next one, lead and copper nitrate. So again, copper and lead will switch places. So we're going to end up with copper and lead nitrate. So if we look on our table, on our activity series, we see that copper is down here and lead is up here. So if we put lead into copper nitrate, because lead is above copper, this will react. So we're going to circle this guy because he will react. Okay, because lead is more reactive than copper. Think about it like this. These metals down here at the bottom, copper, silver, gold, platinum, we call these guys noble metals because they really don't like to react. They would much rather be alone. They want to be by themselves. Okay? Just like noble gases don't want to react, noble metals don't want to have a partner either. They want to be by themselves. So if they are a pure metal, they want to stay that way. If they're a solution, right? So if they're bonded to something else, they want to lose that bond and become a pure metal. All right, so magnesium and zinc chloride. So zinc and magnesium switch places. So we have zinc and magnesium chloride, kind of running out of room. So if we look, we see that magnesium is above zinc. So yes, this will react because magnesium is more reactive than zinc is. Okay, next, copper and sodium chloride. So we'd end up with sodium and copper chloride. Okay, we see that sodium is way up here, copper is way down here. So no, this would not react. Copper is way less reactive. It's not going to react. And you've experienced this. If you've ever been to the ocean, which is salt water, sodium chloride, you can wear your jewelry or you could have a penny in your pocket while swimming, and it's not going to do anything. It's not going to react and give off energy and degrade or anything like that. So this reaction would not occur. And then the last one here, gold and silver nitrate. So again, we just switch partners. So silver and gold nitrate. And we see that gold is below silver. So no, this would not react. This equation would not occur. This reaction would not occur. All right. For our last set, we're going to write the chemical formulas only if a reaction occurs. So if no reaction occurs, we would write NR, no reaction. Okay? All right. So this first one, lithium and iron 3 nitrate. Well, let me get to a better list. Okay, so this is the list you have in your notes right here. Okay, so lithium is up here. This is extremely reactive. Iron is down here. So if we put a piece of lithium metal into a solution of iron nitrate, yes, this would react. So again, iron and lithium are going to switch partners. So we're going to end up with just pure iron and then lithium nitrate. Well, what's the formula for lithium nitrate? Lithium is over in group 1. Because it's in group 1, it has 1 electron to get rid of. Nitrate is NO3, 1 minus. It's one of those polyatomic ions. Right? So one of the polyatomic ions I asked you to learn. If we do the crisscross, we bring this one down here, this one down here. We see that our formula for lithium nitrate is LiNO3. Okay? So we're going to end up with Fe and LiNO3. Okay? Now, this reaction is not balanced. Right? I've got 3 NO3s on this on the left side. I only have 1 here on the right side. This is not a balanced equation, but I'm not asking to balance it. Okay? All right, next, letter B says gold and hydrochloric acid. So we're looking at gold way down here at the bottom compared to hydrogen. So hydrogen is way above gold. So because we're putting gold into hydrochloric acid, no reaction. So we say NR, no reaction. Okay. Letter C says chlorine and potassium bromide. Well, we're putting chlorine in. So chlorine is here above bromine. So yes, that will react. Chlorine and bromine are in the same group. That means they follow the same trends when creating compounds. So it's going to look exactly the same. It's just we're going to switch Cl and Br. So we would write Br2 and KCl. Right? Because bromine is diatomic, meaning it's got 2 atoms. Potassium is always 1 plus. Chlorine will be 1 minus. That's a 1-to-1 ratio. All right, next, copper and aluminum nitrate. So let's find over here, where is copper? Copper is way down here. Aluminum is way up here. So because copper is below aluminum, no reaction. Next, silver and hydrobromic acid. Silver is down here, below hydrogen, no reaction. And our last one, nickel and tin 2 chloride. Well, nickel is here above the tin. So nickel will replace tin. So they're right above each other, or they're not right above each other, but they're going to bond the same way. So we're going to have tin and nickel 2 chloride. So you will be expected to do things like this on your test, which will be next week. So you'll have your table because it's in your notes, and you'll be expected to identify which reactions will occur and which won't, and then write the correct chemical formula of the reactions that do occur. Okay, so let's get back to our note pages. Let me just put this out of the way for a second. We'll see that in here in just a second. Okay, so these are, so we've been talking about single displacement reactions. So when we put a metal in a solution. So a solution is typically, for us, it's going to be dissolved in water. So we call those aqueous solutions. So solute is the material that dissolves. Solvent is the thing that does the dissolving. Ionic compounds will dissociate, meaning they break apart into their individual ions. So here we see KBr. And when KBr is dissolved, we have potassium ions and bromine ions. When NaCl is dissolved, we have sodium ions and chlorine ions. Right? They've separated, they've broken up, they have dissociated. So when things are dissolved, when ionic compounds are dissolved, they break up to form their ions. And that's what this next little part is all about, ionic equations. So an ionic equation shows all of the ions in the reaction. Spectator ions are ions that do not do anything in the chemical reaction. Just like a spectator at a football game is not part of the game, they just watch. The same is true for spectator ions. They are not actually part of the chemical reaction, they just are watching. So, spectator ions don't do anything in the reaction. The net, so like here, if we have an equation, so here's my balanced chemical equation. I see I've got AQ, meaning it's dissolved. So if I write the full ionic equation, I see I've got all of my ions have split apart. These ones highlighted in blue are the spectator ions because they haven't changed in any way from the left side of the equation to the right side of the equation. They are still Cl negative, Na plus. They are still the same. We can remove them and come up with the net ionic equation. The net ionic equation just has the ions that do the reactions. And the product has to be a solid, a liquid, or a gas. So, in order to write net ionic equations, the very first step is to balance the skeleton equation. So, for example, if this is my equation here, I want to make sure it's balanced. So, I've got my coefficient in front here. So, step 1 is to balance the equation. Step 2 is to split the ionic compounds into ions. This is called the complete ionic equation. So every time we see AQ, we split that apart because that means it's dissolved. When we do this, when we write the complete ionic equation, we must include the charges. So calcium chloride breaks apart to form calcium ions and 2 chloride ions, right? That's what this little 2 here means, that there are 2 of them. So calcium chloride will break apart to form calcium ions and chloride ions. Sodium carbonate will break apart to form sodium ions and carbonate ions. Right? So Na2CO3. Remember, CO3 is a polyatomic ion. It will stay together. So we just take everything that says AQ and split it apart. Well, this particle right here says S, meaning solid. It is a precipitate. It does not dissolve. It does not break apart. So we leave it as a single material. The other product, we see NaCl, AQ. So it breaks apart because it dissolves. And again, this coefficient of 2 distributes, right? So this means I have 2 NAs, I have 2 Cls. And so that's what I show right here. So this is the complete ionic equation. The complete ionic equation is really long. All of the ions are split apart. Now, we want to identify the spectator ions. The spectator ions are the ones that are not taking place in the chemical reactions. They're not doing anything. They look exactly the same on both sides of the arrow. So, Na shows up as Na plus on the left side and as Na plus on the right side. Cl minus over here on the left side, Cl minus here on the right side. So, because they are exactly the same, we can cancel them out. They are the spectator ions. So we just rewrite what's left, and this becomes the net ionic equation. So the only things that are left are the ions actually doing the chemical reaction. So the net ionic equation. Solubility rules will help us predict whether or not a precipitate will form. If an ionic bond is too strong, that material will not dissolve. And we can determine whether or not the precipitate will form based on our rules. You do not need to know these rules. They are in your notes, which you can use on your test. So we can determine if a solid product will be formed if based on these rules. So anything that is bonded to a nitrate ion, a perchlorate ion, group 1 metals, or ammonium will always dissolve. Silver, mercury, and lead are almost always insoluble. They stay a solid. They do not dissolve. All right, so we're going to just practice looking at our rules. Okay, so we've got a couple of different things that we're going to look at and see whether or not they're going to dissolve. Okay, so let me get a copy of our solubility rules up. Okay, so here's our solubility rules. I'll make this a little bit bigger for us. Okay. All right, so the first thing is we're going to figure out whether or not these guys will dissolve. There we go. Much better. All right, so we're going to circle the materials that are insoluble in water, meaning they do not dissolve, they stay a solid. Okay. So that first one says KBr. Well, K is in group 1. Potassium is in group 1. And our rule says anything in group 1 is soluble. So he will stay dissolved. Next, letter B, lead 2 carbonate, PbCO3. So we look for CO3, and it says insoluble, except group 1 and ammonia. Well, PB is not in group 1, so this will stay a solid. Next, BaSO4. So we find SO4. Our rule says soluble, except for calcium, barium, strontium, mercury, lead, silver. Well, we're attached to barium, so that means it is insoluble. Next, NiCl2. So we find Cl, and it says soluble, except for silver, mercury, lead. Well, nickel is not silver, mercury, or lead, so it will dissolve. Okay, next, letter E, silver iodide. So we find where iodine is, and it says soluble, except silver, mercury, and lead. So this would be insoluble. Next, calcium sulfide. Well, sulfur says insoluble, except group 1, group 2, and ammonia. Well, calcium happens to be in group 2, so this is going to dissolve. Okay. Zinc carbonate. So again, we look at CO3. CO3 says insoluble, except for group 1 and ammonia. Well, zinc certainly isn't in group 1. So this is insoluble. Acetate. That's C2H3O2. So acetate says it is soluble, except for silver. So this would be insoluble. Next, iron 3 sulfide. So we find sulfide, and it says insoluble except group 1, group 2, and ammonia. Well, iron is not in group 1 or 2. So that is insoluble. Next, magnesium phosphate. So we find PO4. Here it says insoluble, except for group 1 or ammonia. Well, magnesium is not in group 1. So this is insoluble. PbI2, well, we find where I is, and it says soluble, except silver, mercury, lead. So that is insoluble. Letter L, KOH. We find OH. It says insoluble except for group 1, calcium, barium, and strontium. Well, potassium is in group 1, so that is soluble. So we will not circle it. And then for our last row, zinc hydroxide. So again, we're looking at OH, and it says insoluble except for group 1, calcium, barium, strontium. Well, zinc is not in group 1, so that is insoluble. Letter N, ammonium hydroxide. Well, anything attached to NH4 is going to be soluble, so it will dissolve. O, Hg2SO4. So SO4 here says soluble except for mercury. So this would stay a solid. And then the last one, Na2CO3. Well, anything bonded to group 1 will dissolve, and it doesn't matter what it is. So that will stay dissolved. Okay. The next part is constructing some chemical equations and determining whether or not what products we would see as a solid material. So remember that in order for a chemical reaction to occur, things have to produce energy or bubbles or change in temperature or change in color or produce a precipitate. So in this case, we're looking for precipitates. We're looking for solids. So we're just going to write the formulas of what the products would be and then determine which ones would be a insoluble product, which ones would be the precipitate. So AgNO3 and KBr. Well, these are double displacement reactions. So K and Ag will switch places. So K and Ag will switch places. So we're going to be left with KNO3 and AgBr. So we look at our solubility rules for Br, or we look at our solubility rules. We see anything that is attached to group 1 is soluble. Anything attached to NO3 is soluble. AgBr, well, Br is soluble unless it's got silver attached. So we're going to box off this guy. So we would see a solid precipitate there. Okay, KBr and BaCl2. So we're going to switch partners. So Cl and Br will switch places. So we'll be left with KCl and BaBr2. So let's look at our solubility rules. Potassium is a group 1 metal. It will always stay dissolved. Okay. Br says soluble unless it's bonded to silver, mercury, or lead. So in this case, there would be no reaction observed because no product is going to form a solid. Okay. Next, aluminum nitrate and potassium bromide. So we'll get KNO3 and AlBr3. Well, we already know KNO3 will stay dissolved. So let's look at AlBr3. So bromine says soluble except for silver, mercury, and lead. Again, we don't have silver, mercury, or lead in this reaction, so no solid product would be formed. And then last, copper 2 sulfate and potassium bromide. Now, when we write chemical formulas, we have to remember the crisscross method. So copper 2 sulfate. So copper is...
Just tell me what you want to be reminded about.
Sorry about that. So in this case, copper is 2 plus. Bromine, because it's in group 7, is 1 minus. So the formula would be Cu Br2. Potassium is in group 1, so it's 1 plus. Sulfate, one of those polyatomic ions you had to learn, 2 minus. I need 2 potassium for every 1 sulfate. Okay. All right, so my formulas are going to be K2SO4 and CuBr2. All right, so let's check our solubility rules. So potassium, group 1 metal, always stays dissolved, no matter what it's with. So that will stay dissolved. CuBr2. So again, we're looking at Br, and it says soluble except silver, mercury, and lead. Well, again, none of those are present, so we would not see a reaction occur. So no solid product would be formed. All right, so now we're just going to do the same thing with the next column here. We're going to do sodium carbonate. So mixing sodium carbonate in with everybody. Silver and sodium are both plus 1s, so they're going to look exactly the same. So we're going to end up with NaNO3 and Ag2CO3. Okay, so all I've done is I've replaced Na and Ag. All right, so let's check our solubility rules. Na is a group 1 metal. It will always stay dissolved. Ag2CO3. So let's find CO3. It says insoluble except group 1 and ammonia. So this is insoluble. So we would have a solid precipitate there. Next, BaCl2 and Na2CO3. So we're going to end up with NaCl and BaCO3. Well, we know NaCl dissolves, right? We know salt dissolves. So let's check BaCO3. Well, CO3 says insoluble except group 1 and ammonia. So this would form a solid precipitate. Okay. Let's do AlNO3. So we're going to end up again with NaNO3 and Al2CO3. I know that this is my formula because aluminum is in group 3, meaning it has 3 electrons it will get rid of. Carbonate is CO3 2 minus. If we do the crisscross, we bring this 3 down here, this 2 down here. We see the formula is Al2 parentheses CO3 3. Okay. So let's check our solubility rules. NaNO3 will always dissolve. CO3 says insoluble except group 1 or ammonia. Aluminum is not in group 1, it's in group 3. So it will turn into a solid. And then CuSO4. So we're going to switch partners again. So Na2, SO4, and CuCO3. Group 1 metals will always stay dissolved. Carbonate says insoluble except group 1 and ammonia. So it will form a solid product. Okay. Calcium sulfide and silver nitrate. So calcium is in group 2, meaning it's going to have a +2 charge. So calcium nitrate is CaNO3 2, because every nitrate is 1 minus, every calcium is 2 plus. And then silver sulfide, which is Ag2S. Silver is 1 plus, sulfur is 2 minus. So let's check. CaNO3 2. Well, anything attached to NO3 is going to dissolve. The sulfur says insoluble except group 1, group 2, and ammonia. Silver is not in group 1 or group 2. Next, CaS and BaCl2. So we're going to have CaCl2 and BaS. Well, calcium and barium are in the same group, so they're going to follow pretty much the same solubility rules. So calcium chloride is going to dissolve, and calcium and barium sulfide will dissolve, right? Because sulfur is insoluble except for groups 1 and 2. And barium is in group 2, so it will dissolve. All right, next, aluminum nitrate and calcium sulfide. So we're going to get calcium nitrate and aluminum sulfide. Again, Al2S3, because aluminum is +3, sulfur is 2 minus. All right. Nitrate will always dissolve. Sulfur is insoluble unless it's group 1 or 2. And aluminum is not in group 1 or 2. Calcium sulfide and copper sulfate. So we're going to get calcium sulfate and copper 2 sulfide. So let's check. Calcium sulfate says soluble except for calcium, barium, strontium, mercury, silver, and lead. So that would stay a solid. All right, sulfide says insoluble except group 1 and 2. Well, copper is not in group 1 or 2. So in this case, we'd actually see 2 types of precipitate. And then our last one, we're going to do ammonium hydroxide. Ammonium is NH4 with a 1 plus charge. Hydroxide is OH minus. So we're going to end up with NH4NO3, which is ammonium nitrate, and AgOH, silver hydroxide. So let's check our solubility. So anything attached to ammonia or nitrate will stay dissolved. Hydroxide. Hydroxides are insoluble except for group 1, calcium, barium, and strontium. So this will form a solid precipitate. Barium chloride and ammonium nitrate. So we end up with ammonium chloride and barium hydroxide. Barium, it's in group 2, it's 2 plus. Hydroxide is 1 minus. That means I have to have 2 to cancel out. All right, anything bonded to NH4 will dissolve. And let's check OH, and it says insoluble except for group 1, calcium, barium, and strontium. So it will dissolve as well. Next, aluminum nitrate and ammonium hydroxide. So we end up with ammonium nitrate again and aluminum hydroxide. We know anything attached to ammonium or nitrate will stay dissolved. So let's look at AlOH3, and it says insoluble, except for group 1, calcium, barium, strontium. Aluminum is not in group 1. So it would become a solid. And then our last one, copper sulfate and ammonium hydroxide. So we end up with ammonium sulfate and copper hydroxide. So we know anything attached to ammonium will dissolve. Copper hydroxide will stay a solid. It is insoluble. So again, on your test, you'll see problems like this, where you have to identify what the soluble materials would be. All right, so let's go back over here. And so here's your homework for section 3.